As we start our third year of weekly podcasts, we thought it would be a great idea to get an update on one of our biggest stories of our second year, the Webb Space Telescope.
And to do that, we welcome back Mark McCaughrean to the podcast, Senior Advisor for Science and Exploration at the European Space Agency and an interdisciplinary scientist for this mission.
Don't forget to get in touch. You can do this via our social media pages at Space and Things 1 on Twitter and at Space and Things Podcast on Instagram and Facebook, or via the contact form on our website.
And please consider hitting the share button to help our non-existent marketing department. But right now, enjoy episode 105 of the Space and Things Podcast.
Oh my God! Unbelievable! But it is great to done.
You're listening to Space and Things with Dave Giles and Emily Carney.
I'm Emily Carney.
And I'm Dave Giles. What a weekend!
I know. Yeah, we just got news that the next weekend's going to be nuts too. So
Absolutely.
I'm still exhausted from. I got plenty of sleep last night, but it was nuts. I'll talk more about that later.
I think we should do it now. To be honest, let's get it out of the way. I think it's the hot topic, isn't it? So let's talk about it now.
That's a good idea. Okay.
So obviously you went over to KSC or the surrounding areas to go and try and watch the first launch of Artemis-1, right?
Yes, I did.
So you went down on Sunday?
Yeah, I went on Saturday night, basically to beat the traffic driving up, the I-4 traffic.
Yeah.
So I did show up Saturday night, and I went to US1 in Titusville, and I went along the water. There were already people camped out.
Wow.
Saturday night. So the next day, everywhere was gridlocked. It was worse than the last space shuttle launch. It was nuts.
Wow.
I've never seen anything like it in my life. It was insane. Me and my group, we just went along US1 in Titusville because that's really the only place we could find room.
Yeah.
Honestly, we probably should have gotten up way earlier than we did. And I was up all night. So anyway, we headed over. Based on, the Twitter updates, I had a feeling that it wouldn't launch that day. So I wasn't really upset when it scrubbed. I was like, okay, it's the first launch of a major, rocket. It's pretty visible. So, I understand, but Engine 3 is now a meme.
Yeah.
Now its own meme. I think Engine 3 has a Twitter account now, which is just nuts. But I feel bad because in a very 2022 twist in this whole story, Twitter has tried to cancel Engine 3. Couldn't help itself, man. It was probably stage fright. We all get it, right?
Yeah. So for those of you who don't know, the launch got scrubbed because Engine 3 of the four main engines, essentially it couldn't regulate its temperature correctly in the same way that the others did. There was a sticky valve, which was stopping it being able to vent some of the hydrogen, which helps keep the temperature where it should be. That's my basic understanding of it. I think that's roughly right. So of course they scrubbed because they couldn't figure out a workaround. NASA just had a little media announcement about what the thing is, and they said the team has rested, they've analysed the data, they've identified what the problems were, and they're now going to try again this Saturday.
Yeah, which is weird.
They originally said the next launch window would open on the 2nd, which is Friday, but they've said they're going to do it on Saturday. So I'm guessing they want an extra day of just correcting a few things, and they figured it would take a day. But do you know what? After that, my hopes are now feeling like it's not going to happen yet. Like, I think we're going to have a few more of these. I've seen a few people say that was essentially wet dress rehearsal 4 or 5. I can't remember where we're up to now. And then the next few attempts to launch are going to essentially just be that, wet dress rehearsals, filling the rocket up with fuel, and seeing this, because this problem was one that they were hoping to test on the last one, but they weren't able to because of another problem. So it's likely that they're going to come to a few more of these little issues over the next few weeks, or it might just go up absolutely fine on Saturday. We shall see, but I'm not expecting it to go up on Saturday.
Yeah, I'm not expecting it to go up, honestly, because it's a brand new rocket. I am not going over Saturday, mainly because I'm still recovering from this weekend.
Yeah.
At any rate, I'll probably watch it from home, and I'll be parked on NASA TV, and I'll just watch it. Depending on the visibility and how good the weather is, I'll watch it from my driveway.
What was the atmosphere around? I know you said the roads were busy, but did the whole area have a vibe of excitement, or did you not get to experience much of that?
Everybody was real excited. It was I think it was a positive vibe. I didn't get any bad vibes that I got off like Twitter. Twitter, everybody was like, oh my God, I can't believe it got scrubbed. Like, are y'all new here?
Yeah.
Like, shuttle scrubbed. You would go there for the same damn launch several times. And I understand, because we've seen what happens when we launch vehicles that aren't ready.
Yeah.
So I did not get any negative vibes while I was there. Like, everybody was excited. The coolest thing for me, well, there was a couple things. One of them is very selfish, but the first cool thing was seeing like little kids, like toddler age kids wearing spacesuits and NASA shirts. I just think it's awesome seeing that. I love it. I mean, who knows? A kid who might see this might be interested in going into aerospace, or even might walk on Mars. You just never know. I mean, it sounds cheesy, but I always think of that. Yeah. But the selfish part was that I saw a few people wearing space hipster shirts, and they didn't recognize me, and I wanted to go up to them, but I was like, man, no, don't be a dork. Yeah, I created that, pat on the back, and they'd be like, ma'am, who are you? Like, get away from me.
I'm the crazy cat lady.
Hey, I'm the crazy lady. Yeah, I'm the nuts person. You know me? Oh yeah, get away. So I didn't want to bother them, but that cool, was cool, because I was like, wow, I don't know who they are, but they have our shirt on. So that's really cool.
I guess also for those of you who, like yourself, who managed to get down there earlier, you at least got to see a launch, right? The SpaceX launch happened as well, right?
Yes, there was a Starlink launch on Saturday night late, and I did get there in time for that. It was really cool because it was so cloudy, it kind of disappeared and lit up the clouds.
Oh, nice.
It lit up the clouds from bottom to the top through the whole ascent. The whole sky lit up orange, but it lit up all the clouds. It was really oddly very beautiful. So that was really cool. And of course we could hear it. It wasn't super loud, but you could hear the rumbly, like, rocket just went up, as it does, and we got to see a beautiful sunrise yesterday, or I say yesterday. It was yesterday. Yeah. We got to see. I'm so messed up because I was up all night. Yeah. We did get to see a beautiful sunrise and stuff like that. So it wasn't like, I left there bitter or mad, because a few people like, were you upset? I'm like, no, I'd rather them not launch, because you got to wait until it's right. Yeah. And I understand that.
We say it quite a lot, but space is hard.
If everybody could do it, everybody would.
Absolutely.
You know?
With the short-term attention span that people have these days who aren't necessarily interested, there was a lot of hype about it. The BBC was sending out news alerts about it, which never happens. I met up with someone today for lunch who was asking me all kinds of questions. It's amazing. We're going back to the moon. It's so romantic. And they're not someone who's particularly interested in it. Had a load of questions because obviously it got that much coverage. So I get that it's frustrating for people who don't follow these things regularly, but it's hard. It's better to delay than to launch and it go wrong. That's how I always feel.
Yeah.
I think all of us feel.
When you're dealing with equipment and people, because Artemis is going to carry people eventually, when you're dealing with that and they're sitting on, thousands of pounds of fuel, you'd rather get it right.
Well, my nephews had tuned in because Shauna Sheep was in there. You wouldn't want to see them. Oh! Yeah, do you know what I mean? To them, that's a big deal. You don't want to blow up Shauna Sheep.
I don't even want to think about that.
I don't know if you remember this, but episode 6, Emily, it's almost 100 episodes ago, we did an episode called No Scrubs where we talked about historic, famous scrubs and aborts. Do you remember doing that?
Yes, I do. It was a couple of years back, but I remember it.
Yeah, almost 2 years ago this week. So for those people who might want to know more about scrubs, why that happened, and some of the bigger ones that have happened over time, check that episode out, episode 6.
So let's get into this week's main feature. The Webb telescope successfully launched on Christmas Day, and after a 6-month commissioning period, the first images were released on July 12th of this year, which gave us a glimpse at the full capabilities of the telescope. They included the deepest and sharpest infrared view of our universe, images of the South Ring Nebula, a group of galaxies called Stephan's Quintet, and the Carina Nebula. Also released on that day was some spectrum data from...
Data.
Data. Also released on that day was some spectrum data.
Data.
Oh my God! Wow.
I'm hazing you a little bit. Don't worry.
Okay. From WASP 96b, which is a planet in another galaxy, and the data revealed that there was some water in the atmosphere of the exoplanet, a huge discovery. Oh,
absolutely.
God.
Since then, data has been streaming out at a high rate. So we thought it would be great to bring back Mark McCaughrean, an interdisciplinary scientist on the mission and a senior advisor for science and exploration at the European Space Agency. We last had him on the podcast on episode 68, which was just before the telescope launched. And in that episode, we found out all about how it should work. So consider this part 2 of the discussion about the Webb telescope. I recorded this interview 2 weeks ago in anticipation of this episode, so when Mark mentions things happening this weekend, they've already happened. We'll update you on that after the interview. Unfortunately, Emily was a little bit under the weather on that day, so I had to undertake the interview on my own, but she did send me some questions beforehand, so it's still very much a team effort.
Well, it may have been one small step for Neil, but it's a heck of a big leap for me.
Hello, Mark. Welcome back, and thanks for joining us again. So after all the worry about the launch and the commissioning process of the telescope, we're now getting real data. How happy are you with what we're seeing so far?
Yeah, I actually had to check and see when we spoke last, and it was 30th of November, I think. So
that was about right.
Just a few weeks before the launch. And I think at that point, I probably didn't even know that I was getting to see the launch because it was due something like the 18th of December or so, I think maybe at that moment. But then as it got slightly postponed and pushed back close to Christmas, in a good way for me at least, all the VIPs started dropping out and they didn't want to go anymore. It's too close to Christmas. And then around the 20th of December, I just sort of put my hand up and said, well, if nobody else is going, I'll go. My family were good about that. We had Christmas Day on the 28th.
Nice.
And we had it on the 25th because I actually shared the rocket launch with them over FaceTime. So that was kind of fun.
Amazing.
But it seems like a long time ago. And as you know, a lot has changed since then. But to answer the question directly, slightly surreal, really. I mean, it's amazing. It's wonderful. But it also just kind of doesn't quite feel real because we've been working on this, different people for different lengths of time. I've been on it for 24 years. And to finally know that it actually worked to begin with, which is astonishing. And the stuff it's delivering is just amazing. I mean, in some ways, it's exactly what was promised, but that doesn't take away the sense of awe when you see it.
Yeah, absolutely. And from what we've had so far, what do you think the greatest discovery is?
I think if you look at the way that the mission is being staged in terms of taking data, so we had 6 months of commissioning, and during that time, you know, if you like, discoveries were the damn thing works, and amazingly well. So, you know, from the purely technical perspective, just seeing the stars, those 18 images from 18 separate mirrors kind of get aligned and get sharpened up, the discovery that that physics works, and engineering works, that was something. And then there was there are a few kind of, well, not leaked, but a few kind of hints about what might be in the background of some of those images where you started seeing galaxies in images of stars, which are there to focus the telescope, but you could see galaxies. And then came the 12th of July, which seems like a lifetime ago, but it's only 6 weeks, where a bunch of images and spectra had been taken as the instruments were coming online. So, you know, the instruments were commissioned sequentially. Some were more complicated than others to make fully work. But when they came online, you could start taking data with them. And those data were sort of stacked up and prepared and ready. And we put a bunch out on the 12th of July. And I think, well, I had not seen them until a few days before. So I had no idea even what was being looked at. Wow. I mean, that was a very tightly held secret, even from the people on the science team. And when you first see them and you kind of lean back, and I should say where I was in the basement of a restaurant, a hotel/bar in London, in Soho, owned by Iron Maiden, of all people. Good friend of mine knew them, and we were having a meeting there anyway. So that, you know, for me, that's where I first saw the images from JWST. It was in Iron Maiden's bar.
Brilliant.
And then we had a week or so to prepare to talk about them. And that was interesting too, because, you know, we were on the spot and I was one of the people talking in public about one of those images from our mission control in Darmstadt. And it wasn't actually one in my specialist area. So I'm a star and planet formation person, and this was Stefan's quintet galaxies. I know the stuff in a way, but I had to think about how to portray it and how to put it across and how to give a sense that it's meaningful.
Yeah.
None of those, in a way, were discoveries. They were a representation that we were ready to go.
Of course, yeah.
So what's happened since, of course, is that, once the floodgates open on the 12th of July, lots of data started getting taken and being released. Some of it is being given just to the scientists that proposed it. So there's a lot of data out there that I haven't seen and I won't maybe see for a while.
Wow.
But some of the programs we had set up were designed to put data into the public domain as soon as possible. These are called the early release science programs. And the idea about that was that the people who proposed for those programs knew they would have to the data would go public immediately. They'd get money in order to be able to work on them. But the idea was that it would allow the whole community to see all sorts of different kinds of data from different instruments and prepare for the next open call for observing time, which comes actually quite soon in January. So those data, as they've been taken and continue to be taken, are going public just like that. So just today, we've seen new images of Jupiter, for example, in the infrared, which, there's some lovely features in there. You see the rings, you see some moons, you see the aurora, you see some strange atmospheric hazes. But what's a bit premature is to say what's being discovered, because these data are being worked on quickly. The one area where I would suppose there has been, well, not controversy, that's too strong, but a sense of how science is done are in the deep field images, those data which are taken to kind of drill a hole in the sky. And they're not as deep as the ones we'll take in the future. They're kind of testing. But we're seeing galaxies all the way to within a couple of 100 million years after the Big Bang.
Whoa.
And what's interesting about that is that they're potentially upsetting the apple cart a bit. The galaxies seem to be getting built up more quickly than you would expect after the Big Bang. Now, some people are saying, the Big Bang theory is wrong. Well, it isn't, and it isn't at all. Maybe there are some wrinkles in the theory to do with how galaxies form. But it's also interesting to realize different people looking at the same data are finding different things. And that's a cautionary note. At this point, not everything's not calibrated properly. Everything's not quite ready. But that hasn't stopped some people going out there and saying, look, this is what we're finding. And the media love that, of course.
Of course. Obviously, that question was a little bit naive. I apologize for that. But you did hint at the fact there's been some surprises. So I wonder if there have been some other notable surprises within the data we've had so far. Obviously, a French scientist did post a lovely picture of some salami suggesting it was Proxima Centauri, which was a lot of fun.
Well, even that, right? I mean, it's August, and what can you expect in the August silly season? So that stems back several years to somebody posting a piece of salami, and then Peter Coles, who's an astrophysicist friend of mine in Ireland, posted it. I commented on it briefly. It got picked up. It went everywhere, and then somebody plagiarized it, and then they got in trouble. I mean, it was it's August. What can you say? Don't release data in August because that's what happens.
Yeah.
What I will say is, I bet you there are some surprises because there's a lot of data. There are accounts on Twitter and other places you can follow where you can actually see what's being observed today, right now, a running commentary on what's being observed. And if you just sit and watch that go past, you think, I bet you there's something interesting in that field, in that galaxy, in that star-forming region, on that planet. And there are data that have been taken on exoplanet atmospheres, for example, and it's been taken because you can see it going through the commentary of the observing sequence. But those data haven't come out yet. And to some extent, that'll be because they're tricky, and we're learning how to work with complicated data from a complicated new machine. In some ways, the data on the distant galaxies, I have to be careful. It's not the easiest data you could take, but at some level, what you're looking at is you're measuring very faint objects in different colors, and then you're running them against models and saying, well, maybe that's a very young galaxy early in the universe that's been redshifted. Mm-hmm. Maybe that's a nearby galaxy which has got lots of dust and it's red for that reason. But many of the other ways of taking data with JWST are much more complicated. All the spectroscopy, for example, will take a lot more work. So it's not that people are hiding the data, it's just it will take time for us to do a decent job on it. So I'm going to duck the question by saying I bet you there are lots of discoveries, but I just don't know what they are yet.
Absolutely. So obviously you said there that one of the big surprises was the fact that it all worked. Despite that, were there any worrying moments within the commissioning process where you thought we might have some serious problems, or did everything go as smoothly as we were led to believe in the public?
Well, I have to be a bit careful because I'm not super close to the day-to-day, mission operations. That was all being done in Baltimore. We were getting daily reports on the science working group, and they were that was all done in confidence. So we were kind of halfway inside, hearing what was going on. And there were There were things where it's like, oh, well, that didn't quite work. The telescope has been hit by a cosmic ray. That's upset the computers. The computers have said, I don't know what I'm doing. So the telescope goes into safe mode. And those things happen, but they always happen when new observatories start running. The one place which I suppose did cause some interest and was released to the public was this being hit by micrometeoroids.
Yeah.
So we're out at L2, 1.5 million kilometers away from Earth. In the solar system, there are these streams of dust particles which are left behind as comets move around. And as we go around the sun, we go through those dust trails. Now, we have a fairly good idea how often a telescope like JWST should get hit, because we've got other missions out in the same place at L2. The Gaia mission in particular has been out there since 2013. And Gaia has been registering hits by dust. So we have a good model for how many dust particles are out there. And JWST got hit by a handful, which were all within scope. So yes, fine, we'll get hit by those. And the whole observatory had been designed with those in mind. And then we got hit by a bigger one that was unexpected in the sense you wouldn't expect to see it very often. Maybe, let's say, once in 10 years or less. That doesn't mean to say you can't see it in the first 6 months.
Yeah.
Perfectly reasonable, but you kind of think, well, that's kind of statistically a bit early. And what we know from that one is that it hit the primary mirror. It hit one of the 18 segments, and it made a ding in it. And that was seen the next day. Because it was still in commissioning, people were regularly monitoring the shape of those 18 mirrors, how they were focusing the light. And it was noticed that mirror, if I get it wrong, but I think it was C2, which is one of the ones near the bottom, was out of family. It had extra what we call wavefront error, which means it wasn't focusing light properly in the same way the other 17 were. Now, it was possible to adjust some of that, to slightly bend the mirror and slightly move it up and down, but not to get rid of the bait. It's not a hole in the mirror, but a little crater. And also it injected energy, because these things, even though they're small dust particles, they're moving very fast. They've got lots of kinetic energy, and it heated the mirror up slightly and bent it slightly. And you can't really take that out. But because all of the other mirror segments and all of the observatory were actually performing better than designed or better than requirements, we're still well within requirements at this point, even with C2 having been dinged. And one way to think about that is we designed the telescope so it would focus light as sharply as possible, so up to the theoretical limit, at a wavelength of 2 microns, so roughly 4 times mid-visible. And below that, we thought the mirrors wouldn't be quite good enough. They weren't polished accurately enough. They couldn't be aligned accurately enough. And we would just take slightly blurred images relative to the theory. Turns out they were actually diffraction limited at 1 micron, a factor of 2 better. So even with C2 having been dinged, if that's the name of the segment, then we're still well above requirements at this point. So I guess the real question at the end of that is, how long will it be before we get hit by another one of those? And if it happens every 3 months or every 6 months, then it gets a bit worrying. But if the next one doesn't come for a couple of years, then all right, we're fine.
Right, so I'm trying to get my head around this. Do you now not use the section of the mirror which is damaged, or is the damage taken into account when looking at the data?
No, imagine the worst case scenario is that, a brick came along and actually blew the mirror segment up. Well, it's 1 out of 18, so it's a 5% effect in the loss of light. Really what's happened is that you're still collecting light on that mirror. It's still almost exactly in the right shape and it's in the right location. It's just a little bit bumpier. So instead of sending the light exactly to where it's supposed to be, there's going to be a bit of scatter on that. But it's only 5% of the light of the total mirror. And it's only a little bit bent, if you like. So it's only adding a little bit of wavefront error compared to the whole mirror. We can't kind of take it out of the beam because we can't tilt the mirrors enough that you would kind of move the star off to one side. And in fact, even if you did, another star which was out of the field, that would come in. So you keep it as aligned as possible. There's no way of actually masking it out at this point.
Okay, I think I'm beginning to understand it.
Well, no, I mean, let's take the time. I mean, ask the question another way and see if I can answer it a bit better.
Okay. So does it require all 18 mirrors to create an image, or can you take out the one segment which has the damage? I'm trying to think of my basic Photoshop skills, right? So they're probably completely irrelevant. But if I've got a lens flare or someone's got red eye, I can get rid of that bit. Is that what the people with the data are doing as a result of this damage to the mirror, or does it not matter?
That's a good question. I mean, the way to think about it is the primary mirror, which is these 18 segments, which build up a 6.5 meter diameter mirror. Forget that there are 18 segments there. I mean, effectively, we've engineered it so perfectly that you can't even see that anymore, effectively, in the data. It's acting as one mirror, which is 6.5 meters across.
Right.
Now, all of the light from the whole of that mirror then gets focused onto the cameras.
Right.
Now, different angles that you're looking into space at are different objects, and they get put into the image in different locations. So the star to the left, the star to the right, the galaxy in the middle. Mm-hmm. They're all using the whole primary mirror to collect the light. So we don't use one mirror for one part of the field, and another mirror for another part of the field. We use all 18 mirrors for all areas of the field. We don't move them, but if the light comes in at a slightly different angle from a star to the left, its light gets focused, if you like, over on the other side of the picture, and so on. So we can't take out that one mirror. And in fact, it's working extremely well anyway. It's just a little bit dinged, and it doesn't make sense to lose the photons there. But there's no way of blanking it out in the digital domain, because once you reach the image doesn't know where those photons came from anymore. All 18 have all added up together, and they're all there. You can't tag a photon and said, oh, it came from segment C2. A way of thinking about it is if you had an SLR camera and you actually restrict the amount of light coming through the camera by changing the aperture, right? You have a bladed circle inside which you zoom in and out. It doesn't change what the image looks like. It's still a full image. You just get more or less light coming through, right? That's what the aperture stop is for. And that's what would happen here. If that C2 segment was completely broken, then we would just lose 5% of the light. We'd have a slightly dimmer image, but it wouldn't be a part of the field which was changed. The whole field will still be there.
Right, yeah. Now I understand. Thank you for taking that time and helping me out there. Right, so obviously the response to the first images was huge, right? Front page news all over the world and all kinds of crazy things. I'm pretty sure Coldplay used the images in their stadium show the night they were first released. Yeah. How worried were the team about whether the public would grab onto it like they have done previously with Hubble images, for example? Was there some thought given to what the first images might be with regards to public relations?
Yeah, that's a great question. And again, because I wasn't on the inside of that team, the so-called early release observation team, they were sort of, I'm sure that, of course, they thought about it, and they thought about it for a very long time. And they took more observations than were released then. So they were also looking to see what would look good and what wouldn't. And there would be some which may get released later. There was only room for a limited number on the day to keep the show, if you like, limited in length. So they had one level of anxiety, I'm sure, about picking the right objects. And those of us on the science team who were actually outside that process, I mean, it was very, very tightly held by a few people in order not to have any leaks, right? Mm-hmm. So we were second guessing what they were doing with no knowledge whatsoever, which was a bit interesting when we were in the room with some of them sometimes, sort of saying, have you picked the right targets? And they would just stare at us. What's really interesting is that I suppose there are layers and upon layers of what you're used to seeing, right? Mm-hmm. So I will fully admit that when I first saw that Carina image, and again, that Carina image, which is this gas and dust star-forming region with blues and golds and so on, the first time I saw it was down a WebEx link in the basement of Iron Maiden's hotel. It wasn't the greatest of images at that point. We weren't sent the actual images until a few days later. I have to say that my reaction was a little bit underwhelmed because it's like, I've seen all this before. This looks like Hubble.
Yeah.
And without naming names, a few of us, in and around, felt the same thing. And we were kind of thinking, ooh, is this really going to work? Now, some of the others were clearly, going to work from the outset, like the gravitational lensing deep field, right? The SMAX cluster. And the exoplanet spectrum was something where people could say, oh, there's water. Wow, right? But the Carina Nebula image, and to some extent the Stephan's Quintet, I think my first reaction was there's a danger that people are going to say, looks just like Hubble. What's new here? I mean, I admit that I'm completely wrong about it, because I think people did really engage, partly in a good sense, because when you blow the images up and you get them in full res, I mean, my goodness, there's amazing amounts of detail. And one of the things I did for the image that we put out on the day, the one we were given to talk about was the Stefan's Quintet, is that I made a kind of a drift around the image where you could zoom in and see some of the details. And I think that helped. Notably, the night before, when President Biden showed the S-MAX deep field, they never zoomed into it because it was such a short broadcast, and they kind of showed it at the end of the room. And I think people were straining, thinking, well, what am I seeing here? But when you see the image and you could blow it up and start walking around it, I think it really becomes obvious how amazing it is. And also, by comparison with previous images, you go in and look at the Hubble image of those regions. You go in and look at the best ground-based data, and you see just how well JWST is doing. But we've all become very used to seeing beautiful color images on our screens from Hubble, but also from amateurs as well. I mean, amateur observers take amazing images. Of course, their images don't have the same resolution or the same depth, but to the visual, it doesn't matter. It's how big it is, how colorful it is, how much detail there is. So yeah, I was a little worried, and a few other people were. But also, and this is slightly a negative thing, the public actually have a relatively short attention span for some of these things. And I think if they were told that these were amazing, at some level they said, well, therefore they're amazing. There's no criticism implied there, but we're bombarded, we're saturated by imagery, we're saturated by hyperbole, we're saturated by this is the most amazing thing you'll ever see. And that was a danger as well. If you over-talk these images up, there was a danger that people at some point would say, enough already.
Yeah, so true.
And there were definitely different ways of talking about it on the different sides of the Atlantic. And I won't go in too far there, but having talked to many people afterwards, kind of audience responses to different ways of talking about the data got different responses. So I think, our aim at least was to be pretty low key, pretty factual, and talk about what they enabled in terms of science and let the pictures speak for themselves without too much of a kind of, it's awesome stuff, which is not very British anyway.
Absolutely not. Right. So, one of the things I struggled to get my head around the most when these first images came out was this gravitational lensing theory thing. Can you help me to break that down in a way where I can understand exactly what's going on there?
Indeed. So Einstein, one of his key discoveries was that light is actually bent by distortions in space-time. Now, that's already gone quite far. What the hell is a distortion in space-time? Well, it's to do, in a sense, with mass. It's to do with objects. So if I've got a lump of metal sitting out in space, light coming towards that object will be slightly bent because the space-time, the fabric of the universe around that object is actually being distorted, being bent by that mass, by that object. And there's a link between, space-time, I never remember the phrase, but space-time distorts in reaction to mass, and it's the bending of space-time, which is the gravity, which is, then pulling you in. I'm not a cosmologist or a gravitational physicist, but so in that sense, Einstein said, if there's mass in space, space-time is going to respond to that. And the experiment that was done by Eddington was to show that during a total solar eclipse, that the positions of certain stars, which of course are beyond the sun, out of our solar system, would be bent out of place when they got very close to the edge of the sun. You can't do this experiment when it's daytime because the sun's in the way, but when you block the sun off with the moon, suddenly you can take nice photographs of the dark sky. And Eddington showed that, as Einstein had predicted, that gravity, so the bending or the distortion of space-time due to the mass of an object, will bend light. So that then leads to the prediction that if you put a big chunk of mass out in space, let's say an enormous galaxy cluster with billions upon billions of solar masses of material, that the mass of that cluster will actually distort light that's coming from far behind it towards us. And instead of the rays of light coming straight past that cluster in straight lines, that if you arrange it just right, they'll actually bend the light towards you. So like a lens, focusing the light from a distant object, bending around that big galaxy cluster and being focused towards us. And that has two effects. One is that it makes the objects brighter than they would have been normally, like a lens does. A lens focuses the light and makes it brighter. And it also distorts things, because the lens in this case is not a perfect lens. It's not a beautifully shaped piece of glass that's in exactly the right shape. It's a big lumpy galaxy cluster. And so a gravitational lens, like the one seen in that image, effectively is a big lump of material kind of halfway between us and the stuff in the background. And the stuff in the background, which you normally wouldn't be able to see, the light is going past that cluster but gets focused towards us. Suddenly it's much brighter. You can see things. The objects are magnified and they're distorted. And typically you get this kind of concentric set of circles of objects in the background, kind of in arcs around the cluster. And what's interesting is, and you can see that in the SMAX image, you often get multiple images of the same background object, just with different shapes and different locations. And by actually using that information, saying, oh, this is actually the same galaxy seen 8 times in the image, you can say, well, obviously, if it was a perfect lens, I'd only see one image, right? Because it would be focusing the light perfectly. But there's 8. And they're in these positions, and they have these magnifications, and they have these brightnesses. You can actually use that to work out where the mass is in that galaxy cluster, the one that's halfway there. And most of that mass is not in the stars, it's in dark matter. The gravitation of that cluster is dominated by the dark matter. So you can use this lensing as a way of measuring the dark matter profile of the intermediate galaxy cluster. But in this case, what it's really important that it does, it allows you essentially to probe much further back in space to see much fainter objects than you would normally see, because it's magnifying these objects. And that then allows you effectively to probe further back in time, closer to the beginning of the universe.
Okay, so when an object appears 8 times, are we seeing it from different angles and therefore getting different perspectives on those objects? Or is it just the light has moved into a different place?
It's moved into a different place is the way to think about it. So that light, I mean, yes, the light has to be at a very small different angle. If you like, the light coming straight towards us through the middle of the galaxy cluster is seen at a slightly different perspective to the light going slightly to the left or slightly to the right. But the distances are so enormous and the angles are so small that there's really no possibility of getting a 3D view. But again, you will see different magnifications and different distortions. It's a bit like, if you get a glass of water and you put it out in sunlight, that also will kind of lens the light. And you get these things called cusps, where you get a very bright set of arcs where the sunlight is. It doesn't just create one sharp image. It can create a line of very bright sunlight. And that happens in gravitation lensing clusters as well. And if you get an object which sits right on one of those cusps, the amount of magnification is enormous. I mean, they don't lie physically on the cusp, but in the background, their light comes through there. And that was actually used to detect this object before JWST, this object called Earendel, potentially the most distant star ever discovered in the universe. And that was discovered with Hubble. But it's a target which JWST has gone to look at and we'll be getting a spectrum of soon to see if it's confirmed. It's just one star, but it got so enormously magnified by this gravitational lensing that you can actually see it more than 10 billion years back in time.
Yeah, that's mental. Now, the one bit from the original release, which I think got overlooked, was the exoplanet data, because obviously it wasn't a pretty images that could be on the front page of a newspaper. Yeah. Personally, I think that the exoplanet studies could wield the most important results in the life of this telescope. I know you're probably a bit biased given your field of study, but do you have an opinion on what area of study might be the most important, or is it just far too early to say?
Yeah, I think so. And I think there's a bit of a story there to be told about the exoplanets, actually, because when we first started talking about this mission, and the very first discussions were in the mid-'80s, and the first exoplanets were only discovered in the mid-'90s. So what was then called the Next Generation Space Telescope, NGST, and then is now called JWST, was never envisaged to be used for this kind of science at all. Now, by the time that we kind of got down to the nitty-gritty and started making things in 2002, yes, there were lots of exoplanets, but the field has blossomed enormously, and the response of the community has been to apply in spades for observing time. So roughly 30% of the observing time in the first year is going to exoplanet science.
Wow.
And that's effectively a blind peer review. It's the community saying this is what we want to spend the time on this mission doing. Of course, there's lots of time going to distant galaxies, star-forming regions, more nearby galaxies, planets in our own solar system. But the exoplanets really do look to be something which is will deliver some quite amazing results. What people have to realize, there are kind of two things that we can do with JWST. One is actually see the planets, image them, but it's not the best instrument you could imagine for that, because it's only 6.5 meters in size. If you want to see really faint things next to very bright things, you want the biggest possible telescope, and you need some very clever optics to suppress the light of the bright star. When I say big telescopes, we're building telescopes up to 39 meters in diameter on the ground, right? The extremely large telescope of the European Southern Observatory in Chile. So JWST will definitely see some exoplanets. Typically one's further away from their host star than the Earth is, out Jupiter and beyond. But what it can do very, very well is look for those particular cases when planets move in front of their star from our perspective. So, of course, that won't be the case. The alignment won't be right. But we know of lots and lots of planets already where the alignment is right. So the planet passes in front of the star. And as it does so, the planet blocks a little bit of light of the star. So the star's brightness, if you monitor it very carefully, will go down by, let's say, 0.5%. What's interesting is that will be slightly different at different wavelengths, and that's if the planets have an atmosphere around them, so not just a solid rock like the Earth, but we have an atmosphere, and that atmosphere absorbs different wavelengths differently. So, for example, if you look at our own atmosphere, it's very transparent in visible wavelengths, but it's not transparent in the infrared because of water in the atmosphere. So if you looked at the Earth that way, the Earth would actually look a bit smaller at visible wavelengths than it does in the infrared when it moves in front of the star, because when it moves in the infrared, the atmosphere would be blocking the starlight coming from behind. So it would actually make the planet look a little bit bigger in that particular wavelength, which is due to water. And that's what we're doing with JWST. By looking at how much fainter the star gets at each wavelength, we can see which gases are absorbing more or less light and making the planet look a little bit bigger or a little bit smaller than just the rocky body on its own. Or, of course, if it's a gas giant like Jupiter, its size might change quite a lot as a function of wavelength. And that's what we're doing. And that's what that spectrum showed, that one planet, WASP, whatever it was, actually has water in its atmosphere. Now, in that case, it's a very hot planet. It's close to its parent star. And that water is steam. I mean, it's at very high temperatures, but it still says there's water there, water molecules. And you're going to start seeing a lot of that stuff coming out. So there are lots and lots of programs in the first year looking at various kinds of exoplanets, different distances from their host stars, different masses. So some of them will be kind of like rocky bodies, some will be gas bodies. I think we're in for some big surprises there, which is exciting, because that answers the question another way, right? The most amazing discoveries from JWST, if history of any other mission we've ever built like this is anything to go by, will be the things we haven't even thought about yet. Because when you build a machine which suddenly opens up a massive amount of new space to explore, that's when you discover things. So ask me again in 5 years' time, and the answer will be, didn't even see that coming. That was the thing.
That's the exciting thing about all this, isn't it? We don't actually know what the future will bring. What we learn on the ground from other telescopes or other fields of study might completely change the data we're even asking JWST to collect, which could open whole other areas of study, right?
Yeah, completely. And I think, you open up an important point there, which is people sort of say, well, we've got JWST now and we've had Hubble. Why do we need telescopes on the ground? They're very complementary to each other. So, even though you would say JWST is in a great place, it's far out in space, it's above the Earth's atmosphere, it's only a relatively small telescope. There are things where you need to collect so much more light in order to, say, break that light up to make a spectrum and analyze the object. So JWST and the big ground-based telescopes, the next generation now, so the 39 meters, the 25 meters, the ones we're building today, they don't make each other redundant. It's really important we have them together, because there will be things that JWST can discover at the faintest limit of its own images, which it actually won't be able to take a spectrum of, but we will be able to do it with the big telescopes on the ground. But we never would have known where that object was in the first place, because the big telescopes on the ground only have a very small field of view, and they would never have been able to look for those, survey around and find those faint objects.
Yeah, of course. Right. And finally, you said you've been working in this for 24 years. So how good does it feel right now that it's actually happening? Have you had that big emotional release that I would get when I release an album or something like that, that feeling of pride or whatever it is.
It's been interesting. I think if you were involved in a planetary mission and you kind of got to a place on a day and took that first picture on the surface of Mars or landing on a comet, that kind of thing, I think you would say that would be the day. The thing with JWST is there's lots of those days. The launch was unbelievably emotional. I didn't think it would be. I've seen rocket launches and we know that's only the beginning, and yet you're there 5 kilometers away and it goes and you think, wow, that's something. Even the first sharp images, which are engineering images to those of us who are close to the mission, or even that seeing the telemetry of the sun shield opening, right? I mean, that's just astonishing. So I would say that those images on the 12th of July, they're not as emotional for me personally as what will happen this weekend, which is the first images I programmed this telescope to look for 20 years ago.
Oh, wow.
The things I have said I want to look at. And the thing we're hoping for, well, not hoping for, it's scheduled for Saturday or Sunday this coming weekend, is a very young star, completely invisible at optical wavelengths. It's embedded in the gas and dust that surrounds it. But in 1990, we actually made an interesting mistake. We were on a telescope in Hawaii with a pretty primitive infrared camera by today's standards. But that was my career. That's what I did, was build and work with infrared cameras. And a colleague phoned from Germany, and it's 1990, remember? So he actually called from a call box, and he was calling Hawaii from Germany. He was banging coins into the coin box, saying, "You need to look at this object." And we're going, "What? Which object? What?" And his money ran out, and we got the name of it. You didn't have the internet in the same way in those days. You didn't have online catalogs. We couldn't immediately look at. So we went to the big printed book, which I have right here. It's still here in my office. And we, thumbed through and went, "Oh, where is it? Oh, it's that object." And it wasn't. It wasn't what he meant us to look at. It was an object nearby, but not in the same field. And we pointed the telescope at this object, which had been discovered in 1974 as a very bright. And we took a picture, and there it was. It was bright because, hey, it had been discovered in 1974. But near it was this beautiful linear outflow structure. So a jet of gas and dust being emitted from a young star. And it was the first time that had ever been seen, Amazing. That object and that kind of object. And we just sat there at a telescope and went, well, that's cool. Let's forget about the other thing that our colleague said we should look at. Let's look at this. We spent the rest of the night taking pictures of that. And that was in 1990. And that's what I'm looking at on this weekend. And JWST will have 10 times more detail, more spatial resolution. It will see much fainter stuff. It will have seen it move in the last, more than 30 years, because these jets are expanding at 100 kilometers a second. So we'll actually have seen it. We'll be able to make a movie of it. In a way, you're a few days too early, because I suspect that will be very emotional.
It's such a great story. And it actually goes to the heart of the question of what will be the greatest discovery as well. Probably something that was a mistake, something that wasn't even supposed to be looked at, but then made everyone stop and say, wait a minute.
Well, I mean, it could be, although, I will say this, that one of the... it's not a disadvantage, there are very good reasons for it, but it's actually not so easy to just go to a telescope anymore and point to random bits of sky, even by mistake. Telescope time's so precious that, it's very difficult to do that. And it's something I kind of miss from the old days, was, a bit more cowboy, right? We're at the telescope, we got a telescope. Nobody's going to tell us what to do. Let's go and look over there. And of course you will make discoveries, and there'll be many made, but that kind of random lunacy of just pointing at the wrong coordinate in space and discovering something, maybe those days are gone, but we'll see. Maybe somebody prove me wrong.
Yeah. Well, I hope that this is a wonderful weekend for you, and I hope that there are many wonderful weekends and moments coming up for you as well. Thank you so much for taking this time for us and to give us this update. It's such a crazy time. What a crazy few months this one program has had.
Absolutely. And, and this first image comes this weekend, and then in 6 weeks' time or so, I'll actually have images right in the middle of the Orion Nebula with all of the baby stars and stuff. And that's, that's what I'm going to look at. And we're getting ready for that too. So
fantastic.
Yeah, it's an amazingly exciting time.
It really is. Well, enjoy it. And thank you so much for this.
Thank you very much. Thank you.
Hey, congratulations. This is real good.
I just think he is so good at explaining really complex things. I loved how he broke things down for me there. When I didn't understand something, he found a new way of explaining something complex. And I hope that our listeners also pick up on that. He did it last time round as well. Just an update on the data that Mark mentioned he was excited about seeing, as it's the first bit of data he's been working on directly. He tweeted this yesterday on the 29th of August. He said, "A day to remember, my first evening looking at #JWST data for one of my own projects. Images of an object we discovered in 1990. Stunning. Genuinely thrilling. Grateful to so many. Looking forward to sharing when we've had a chance to work on the science." So if you're interested, I'd suggest that you give Mark a follow on Twitter at Mark McCaughrean. If you're unsure of the spelling, just check out our Twitter feed this week. I'm sure I'll be tagging him, or just check the show notes for a link. As always, the video, the full interview unedited, will be up on our Patreon page, which is patreon.com/space and things.
Fantastic, sports fans. It's trench time. And mark it. Copy that.
Okay, a week where delays appear to have been the main focus, but we did have 2 launches, one in China and one at Kennedy Space Center, as we mentioned earlier. As always, you can find the details of the launches, their payloads, and any videos in our show notes on spaceandthingspodcast.com. The Kennedy Space Center launch was a SpaceX launch, putting some Starlink satellites into orbit, which we've, of course, mentioned numerous times over the course of this podcast. This is the SpaceX constellation of telescopes, which will be delivering broadband back to the ground with the aim of eliminating dead spots on the Earth. Well, this week, SpaceX and T-Mobile announced that they're teaming up for a connectivity plan called Coverage Above and Beyond, which will enable you to receive Starlink service directly on your smartphone sometime next year. However, this is dependent on the rollout of the next generation of Starlink satellites, which require SpaceX Starship rocket to take them into orbit because they're a bit heavier. So I think it's probably fair to say that the target of next year might be a little bit premature when we haven't even had the first orbital test of that rocket yet, but we shall see.
While we're talking about delays for upcoming missions, Boeing's first astronaut mission for NASA using their Starliner spacecraft has been pushed back to February 2023. At the earliest, it was hoped that this could happen in December, but technicians need more time to address some of the issues which were identified in the uncrewed test flight, which happened in May of this year. This February target might change, though, as there are already 3 crewed missions to the ISS planned for the start of 2023. The SpaceX Crew 6 flight for NASA, Axiom Space, second private space flight to the station, and a Russian Soyuz flight, as well as 2 robotic resupply missions. So expect some more delays there.
Yeah, and while we're talking about traffic jams on the International Space Station, SpaceX have announced the delay of the launch of their Crew 5 mission for NASA until no earlier than October the 3rd. They had been targeting the 29th of September, so it's not a huge delay, but the date is to allow for extra separation with the spacecraft traffic to and from the station. The crew for this mission includes NASA's Nicole Mann and Josh Quesada, Japanese astronaut Koichi Wakata, and Russian cosmonaut Anna Kikina, who will become the first Russian to fly on a private American spacecraft. This isn't the first delay to this mission, and just to go along with the theme we had earlier, that space is hard, and this story definitely shows how delays can happen, the booster which was going to be used, the Falcon 9 rocket which was going to be used for this mission, was damaged whilst it was being hauled from the SpaceX factory in California to the company's test site in Texas. It hit a bridge.
Why am I laughing? I'm sorry, that's not funny. Oh my God.
But it's a crazy story, right? We often forget that these are huge vehicles that need to travel huge distances, and there are many obstacles for items this big, right, that can cause harm. So the slightest knock to these things can cause catastrophic incidents, as we know. So it's always better to delay, and this just is one of the things that can just show to any of the companies, it doesn't matter who they are, they can all experience different things that are going to cause delays.
Yeah, it could be all sorts of crazy stuff, really. It could be as something as dumb sounding as we hit something in traffic or something.
Absolutely, yeah.
Looking ahead, some big news about the future of commercial spaceflight. A private space station called Orbital Reef, which is a project involving Blue Origin, Sierra Space, Boeing, and a number of other companies and institutions, has passed its system definition review with NASA. This means that it has been deemed that the architecture of the station is sound, and the project can now proceed further into its design phase. The timeline proposed currently has them on track to start operations in 2027, according to the members of the team involved. Let's go. I'm ready for a ride. I'm ready.
Yeah. When you read these dates, though, but bear in mind what we're going through now, does it not just seem a bit silly that they announce dates?
Yeah, exactly. Like, whenever I see dates, I'm like, yeah, just tack on like 5 more years.
Yeah, exactly.
Yeah, 5 more, put on 5 more years to that and maybe, you know?
Yeah, absolutely. And finally, a piece of news which concerns Emily's employer, Celestis. This got quite a lot of widespread coverage, which is pretty cool. I'm sure it kept you busy last week, Emily.
It did.
It also links back to our episode a few weeks ago with Celestis co-founder Charles Schaefer. We had him on to talk about the passing of Star Trek star Nichelle Nichols. Well, her cremated remains and a DNA sample will go to space on the company's upcoming Enterprise flight, which will be the company's first ever deep space mission, which is very cool. The launch will take place later this year, appropriately on a United Launch Alliance Vulcan rocket, and the mission will also include some remains of Star Trek creator Gene Roddenberry, fellow Star Trek actor James Doohan, and more than 200 other flight capsules containing created ash remains, DNA samples, and special messages from clients around the world. So a big week for you guys, big announcement that.
Yes, it's been really exciting, and it's really an honor to contribute in a small way to getting this magnificent woman to space. You know, I mean, she was such a pioneer and really an icon, you know, a TV icon, a space icon, a civil rights icon. I mean, just, you know, and it's really cool to see she's going to do this for real, you know, so I'm so excited. I can't wait to see that rocket lift off too, because Vulcan is really beautiful. I plan on being there to see that. I'm really excited.
Where's it launching from?
It is launching from Cape Canaveral Space Force Station.
Were you expecting the big media coverage that this got? Because it really did blow up a little bit, didn't it?
I'm honestly kind of overwhelmed by it. I knew we'd get, obviously, some press from it. It really speaks to what a superstar she was and how influential and how much she really impacted not just television, but the world.
Yeah, absolutely.
That's it for this week. We hope you enjoyed finding out more about the Webb telescope, and we'll be back next week with more from the world of spaceflight. Who knows? Maybe Artemis will have launched by then. We'll cross our fingers and see. We'll obviously have more about that next week if that does take place. Obviously, we'll keep y'all updated.
Although I'm sure they would have seen on social media.
They would have figured it out.
We'll discuss it either way.
We'll discuss it. Yeah, I'm sure, you know, if you live in Florida, if you saw a big-ass rocket launch out of your window, then you probably figured it out. But still, we're still going to talk about it. So thank you for listening, and we thank you for all your support.
Absolutely. And don't forget, in space, no one can hear you stream.
Space and Things has been brought to you by And Things Productions.